Hello, this is going to be a video on Dijkstra's shortest path algorithm in Excel. So I'll try and explain what this is. It comes from graph theory, and you can have nodes. So this is a graph. So say we have nodes, these are positions like A, B, C, D on a map, and the lines represent distances between them. The question is, if you start at A, how long does it take you to get to F or E or D? And what is the shortest possible time you can get there? So the way that you basically solve this problem is you take A as your initial path here with a distance of 0, and you look at all the neighbours of A. So A can go to B with a distance of 2, and it can go to D with a distance of 8. So you then generate kind of a table. You know, the distance to B is 2, the distance to D is 8. You then go from those places to all of those possible neighbours and look at the distance. That might also go back to A, and then you collate a new list of your shortest distances for all the nodes you've visited. And you keep doing this iteratively until you can find the shortest path to each node. So I'm going to show you the lambda I've built to solve this problem, and then I'm going to talk about how I've made it really, really fast and efficient, and some of the difficulties in doing so. This is the lambda I have built that solves this problem. So distance maze, we could take a map, and this map must have overlaid distances of how long it takes to travel through the cell. We then have our starting node, or starting cell address, if you like, which is E30 here. What that will do is it will spill out a map, and E30, which is this yellow 0 here, obviously has a 0 distance. And we can see that to travel around it, we have kind of this square, which lines up with this one. And then the paths get a bit more complicated because we're iterating over this to find the shortest possible one each time. I've color graded this to show kind of, how long it takes to get everywhere. This cell up here is how long the lambda takes to run, so it's 0.1 seconds to do that. I can also put in multiple starting locations, so I could start at E30 or T10, and obviously we have a 0 in both of those locations, so now the distances have changed. The next argument I have is target cells, so I can put in, AB8. How long does it take to get to AB8? It takes 24, a distance of 24. This also takes an array. So to get to AB8 is 24, and to get to S22 is 28. Finally, let's just go back to our map. Well, not finally, but next, I can turn off diagonals. So let's turn off diagonals there. And now the shape of the map slightly changes. And then the final thing is I can add custom directions. So if I said we can only go diagonally with these directions, it will show a much different picture. And actually, if we started from somewhere else like T11, I think there are many places we wouldn't be able to get to, which are denoted by an X. So let's just go back to our standard format, and then I'll talk about how this works. Another thing I can do actually is block out locations. So if this was water or something, it would block out those locations and say, we can't walk on them because we didn't put a distance in them, and so on, like that. So it's very flexible and it's quick. It might look a bit slower as I'm doing this because I actually have a less efficient lambda in this sheet as well, which I want to compare with later. So let's quickly talk about some of the problems in doing this. If you were to do this from first principles, you basically want to take your starting cell, all the neighbours, and calculate how long it takes, and get a running table of each cell address and the distance it's taken to get there. You would then take all of those cell addresses and move to everywhere you can again, and see if the distance is shorter. If it is, update it. If not, leave it as is. And you'd iterate this process. The problem is, you would iterate, here you'd have 1 cell, here you would have 10, and then it just grows kind of exponentially, and Excel gets bogged down and cannot do it. So I'm just going to put the full lambda into this cell, so you can see what it's doing. And let's put end, which is our last argument. So I am essentially, this is a recursive lambda, so it knows when to stop. And the stop condition is when there are no more places you can possibly visit. To make this efficient, I've basically used a lot of VLOOKUPs because it's the fastest lookup. If you can massage your data into being ordered, sequentially ordered, then you can have what's called a binary VLOOKUP, which is extremely fast. And I'm also binning a lot of locations which are not possible to go to in my interim steps. So instead of going through these lines, I am going to show you the first 2 steps kind of old school cell by cell style. So let's just close this and explain how this was built. So let's go over the first 2 steps of this algorithm. So this here is our possible movement directions, and this is denoted by 1,000,000 for the row and 1 for the column. So a direction of 1,000,000 is moving down a row, direction of minus 1,000,000 is moving up a row, and so on. Throughout the lambda, we are going to iterate through a frontier, which is the most recently visited cells, and a pool, which is a running table of all cells and the minimum distance to get there. So our first step is to look at our frontier. So this is the most recently visited cell, and at the start it's this row 30, column 5, this 0, and it has a distance of 0. We've set that as our starting cell. We then add on all of these directions and 2-col it. So this is all the possible places we can go. So we can go to row 31, column 5, which would be here, and it will basically give us these 8 locations. Next I have the row, so this is just dividing by 1,000,000 and taking the first number, so this would be row 31. The nuance here is I'm minusing 3 because my map starts 3 cells down. In my actual lambda, I've accounted for that so that the map can be placed anywhere and it will still give me the right distances based off the cell address. I use these to index the map, so I try to pull out row 28, so this would be 1, 2, 3. So this, although it's in row 30 of Excel, it's row 28 of my map. And I do the same for column, which is to do mod this of 1,000,000, so it's just going to give me the last digit, so row 28, column 5. This FD is our frontier distance, and again you'll be able to see all of these up here if you want to take a screenshot of this quickly. This is FD frontier distance. I've named everything the same to make it understandable. This is the distance of the cell we are coming from. So we started at 0, so the cell we're coming from has a distance of 0. Our previous distance is the distance we had before for that cell. So we look for it in our cumulative pool, and if we find it, we're going to put it there. If not, we're going to put an X. Our new distance is then indexing the map on our row and column. So our new distance for this cell is 3, which is this one, and so on and so on. So we're just pulling out that map. I then have an interim frontier, I'm calling it. So what I'm saying with this one is if the address is not in our map, just give me 0, 0, H stacked across. If it is there and the new distance plus the distance we had before is less than the previous distance, then give me the new cell and the new distance, which is 3. So it's just H stacking these across basically. If we ever had something where the new path to the cell was a bigger distance, it would not put it in here. It would give me 0, 0. So for example, if I just show you here and I put an X on the map, well, these are not a number on the map, so they're not valid locations. The next thing I do is I sort those, and this is quite crucially important in getting it to run fast. I sort by the first column and then the second column, and this is ascending and this is descending, because when you then do a VLOOKUP on it, you don't need to do an exact match. You can do an approximate match and it will always pick out the right values. My new frontier is then to take the unique cell addresses here, because there may be duplicates, there may be many ways to get to a cell. It bins off any duplicates and only gives me the shortest distance in a possible row. So this is my new frontier that I can iterate from next time. So these are new, shorter distances than we've found before. Because we've found a shorter distance, we should only check new cells from that place, that new frontier, to iterate across this. So it means at each step we're binning a lot of stuff that we don't need, and that's what makes it efficient. My new pool is then anything in the existing pool, stacked with anything in the new pool, and again I need to sort that in the same way as before. So I sort that by here, column 1, then column 2, and ascending, then descending. And again, at this stage, I also have to bin off anything new that's shorter, because in my pool we might have something that's quite big, and we now have a shorter distance in the new frontier, so we need to get rid of what was in the existing pool and replace it with the new frontier. Okay, so hopefully that makes sense. I'm just going to put these back to some distances. Let's pick 3, doesn't matter. And then our next iteration, we're going to do the exact same thing again, but from our new frontier and our new pool. So this is iteration 1. Now let's look at iteration 2, down here. Okay, iteration 2 is exactly the same thing. So I take all of my most newly visited cells, so the last places I got to that were new. I then look at all the new places I can go from there, find the distance of the cell we're coming from, so the frontier distance, find the previous distance we had stacked in the pool, which I actually need to drag these down a bit. I think I've gathered an extra cell somewhere. And then find what my new distance is on the map, which is going to be here. Okay, so this is my new distances. I then am going to say, okay, if our new distance is shorter and it's a valid location, then stack it up, otherwise just give me zeros. So if we just take this first row as an example, we're looking at the cell in row 30, column 4. Our frontier distance, so where we came from, took 3 to get to. The previous distance we had was 3, and the new distance in the map for that cell is a 3. So to get to this cell again, we would have to take our frontier distance plus our new distance. So it would take 6. But we know that we could get there in 3 steps before, or with the distance of 3. And because that 6 is bigger than 3, we don't want it. We bin it off and put 2 zeros. This one is faster. We didn't have a distance before. It was not there, so we have an x. So we now have a new shortest distance to that, which is 6. So it's the new distance plus the frontier distance where we came from, distance of 6. So we do that process and gather all the new possible locations that are shorter. We then sort them, get rid of all the zeros, and only take the minimum ones. Again, there'll be a lot of duplicates in here. I mean, I can see duplicates here already. So we only take the shortest possible ones in our new frontier with this specific sorting method so that we can VLOOKUP into it later as a binary search. And then our new pool is we stack all of our new locations in the new frontier with our old pool and take the minimum ones again. And you'll notice this is sorted in the same way. So that is what we do, and we iterate through it. So I just want to show you, I think Juan Cifuentes, sorry if I'm pronouncing your name wrong, because this was purely inspired by his work, and he did a very similar lambda, but instead of having this pooled set of locations that you iterate through, he iterated a map. So he'd generate the map every time instead of generating the map right at the end. So this is the speed of his, so 0.3 seconds, whereas mine is 0.08, so I'm almost like 5 times faster. Now, his is extremely fast, it's just I've found this VLOOKUP binary search method that makes it a lot faster. The reason I like to use the RC references, I'll just show you his lambda here. He also has a video on it, so I'd highly recommend you watch that. It's quite chunky, which is fine, but the method was really good, and I wouldn't have been able to make it myself without looking at that for like 3 days and trying to understand it. So the benefit of going with this RC method where you label rows and columns with 1,000,000 is it then becomes very easy to just look up the distance. It becomes very easy to change the directions like here, because it's not only that I can put these arrows in, I mean I could put custom directions in. So let's double them up, let's times them all by 2 for example. So this would give me a very strange map. We can only move 2 steps, so we hop over each step. So that just gives you the flexibility that the other version wouldn't have. So I could do stuff like night moves with this, for example. I could denote what a night move is in terms of row column movements, gather all the night moves, and then I could say, okay, these are my movement directions, and we would have a knight, a chess piece jumping around this map, and it would give us the distances for that. So it's quite flexible. I guess the only thing I don't have is like a steps counter, which could quite easily be added, because a question could come up of, you got somewhere and found the shortest distance. How many cells did you step across to achieve that minimum distance? That would be a quite hard question, but if I added a steps counter, it would be quite easy to find out. So I also want to just time this on a bigger map. So I have a 100 by 100 map here. I'll start in the same cell, but this is a way bigger 100 by 100 map. So just to show the speed of this is a timer lambda I have here. So let's change this to be our big map. And let's change this to be our big map. And this is not to say that, oh, look, my lambda's way better. It's just highlighting how efficient you can get this by doing binary VLOOKUP searches, which was very shocking to me. So the other lambda that was really efficient from Juan, if you go and watch his video, it's a really good video, 4 seconds to 100 by 100 map. Now that is really good. With the VLOOKUP, binary search method, you can do it in less than a second, so 0.89 seconds. So let's just refresh and run this again. And a similar situation. So yeah, I'm not sure I can optimize it any more than this. Bo also helped me out a little bit, who's just seem to instantly spot, oh, if you just change this, it will be much quicker. If you just change that, it will be much quicker. Lots of little tips. And I guess throughout this process, I've found out that X match is a little bit slow over many iterations. So is X lookup. So is anything that's not a binary type search. So if you can massage your data and your iterations into being sorted so that you can then do that binary search, it will save you a lot of time on iterations. Okay, so out of curiosity, let's time this on a 200 by 200 map. 8.52 seconds. I wonder if we could go to a 300. This is a kind of an exponential increase in calculation power. And my PC is not the best either, so if I upgraded my PC, I could probably get this about 5 times faster just from having better hardware in here with more cores on my CPU. This PC is about 10 years old now, so to do this stuff, it really has to churn through the data. Okay, 37 seconds for a 300 by 300. I mean, I don't think you can get it any faster than that, and you're not really going to ever see maps that big, especially for this type of challenge. And if you did, you'd probably localize it to a smaller area to force it to work. So 100 by 100 map with this method is less than a second. 200 by 200 map is about 8 seconds. 300 by 300 map is about 37 seconds. With my old 10-year-old PC that is in desperate need of an upgrade, I can probably significantly reduce that. Probably do it in a third of the time with a PC upgrade. So yeah, I'm very happy with how this Lambda has turned out. It was a lot of effort and a lot of people's input to get it to this stage. So there's a couple more other map ones I have in the works. I guess the last thing to say is that you could apply this to things like the flow problem we saw in a case, we're not in Kansas anymore, where you have you know, graph theory and nodes like this, but the lines represent flow, so how much water can pass through a pipe, you know, and so on between nodes. So to do that, you would just have to have a bit of a different layout, kind of a grid of the nodes, but the method would be exactly the same. You would look at all the places you can go, and then, you know, bin things as the distance reduces. So yeah, it's quite fun playing with different things. Let's make this area of the map like more expensive, 40, and we get a red bit, 10. I guess we could put some random other bits in here. Yeah, it's very cool to play around with and see all these patterns that might emerge. Let's change some custom directions to be these. Yeah, it's cool. Anyway, that's it.